Okay, so let's get going on part 2 of today's class. So from here on out, this is all for the final exam. So starting now is where we're covering material that is going to be tested on the final exam. This is basically the last portion of the course. And we are going to start with our look at confidence intervals. So let's set up what confidence intervals are oftentimes used for. And a lot of times confidence intervals are used when you go out of your lab and into the real world. It's used in an application setting when you actually have to put your research into practice. So let's say, for example, that there was a monkey sanctuary. And in this monkey sanctuary, let's say that there was an outbreak of a virus. And for the health of the monkeys, they had to quarantine all the parent monkeys away from their infant monkeys. So they have to split up, parents in one area, infant monkeys in the other area. They have to quarantine these parents because of this virus. They don't want their infant monkeys to go without any sort of comfort or companionship. So these little infant monkeys here, they can't get the real parents, but they can get surrogate parents. So let's say that these monkey sanctuary workers knew about Harlow and Zimmerman's infant monkey studies and knew that you can give these monkeys a little terry cloth mother and they can derive comfort from that terry cloth mother. Now, in the lab, it is enough to progress psychology, to make contributions to psychology, to just know that the infant monkeys prefer the terry cloth mother. That's enough, theoretically, to know that attachment and comfort is important. However, in the real world, there's other considerations, such as budgetary considerations. It's quite possible that because of this outbreak, they've had to spend a lot of their budget on medicine, they've had to spend a lot of their budgets on medical care. They don't have unlimited budgets to buy terry cloth monkeys for each and every single infant monkey. So what they want to know is, how many do we need in order that there is enough terry cloth mothers for our infant monkeys? So they need to know not just that monkeys spend more time with the terry cloth mother, they need to know how much time do these monkeys spend with the terry cloth mother. Because if they only spend 12 hours with the terry cloth mother, then you don't need to buy every single monkey a terry cloth mother. You only need to buy half as many because they can share it over the 24-hour period. So it's important in this situation to know how long do they spend with the terry cloth mother, and that's a new consideration, and that's what a confidence interval will help us determine. All right, I'll give you another situation here. Let's say that there was a car accident that led to the death of one of the drivers, and now the other driver was in court, and their future, whether or not they go to jail, hinges on how fast were they going when the two cars collided. Now let's say that the prosecuting attorney is asking an eyewitness this very question, and they ask, so how fast was the car traveling when it violently and egregiously smashed into the truck? And this eyewitness here has had her memory rewritten. This question has rewritten her memory, and we saw that in the Loftus and Palmer study of hit versus smashed into. Now for Loftus and Palmer, it was enough that they saw a difference. It was enough that they saw that smashed into had higher estimates of speed. But if a psychologist was called in as an expert witness to say, to quantify this testimony that the eyewitness gave, they don't need to know that the eyewitness is now overestimating their memory of the incident. They need to know by how much is the eyewitness overestimating. So that eyewitness that was asked that leading question might have said, cars looked like they were going 60 miles an hour. Now we get an expert psychologist in there, and it's not enough for that expert psychologist to say, well, 60 miles is an overestimation. We need to know how much of an overestimation. 15 miles an hour over? 7 miles an hour over? How much did this memory change because of this leading question? So once again, we see that in the real world application, sometimes you need to know not just that there is a difference, we need to know how big, how much of a difference is there. All right, and the last example here, let's say that you go into industrial organizational psychology, and one day the very big corporation of America calls you in for a meeting, and they've heard about the research that was done on adult timeout, and they want to improve the accuracy of their employees. So they want to implement a 5-second or 10-second timeout condition, and they want to know not just that the 10-second timeout condition is better it leads to better accuracy. They need to know how much higher accuracy is there, because implementing that 10-second timeout condition is going to be expensive. The computers need to be rewritten. We are going to lose productivity because your workers will be on timeout twice as long as they were originally. So those changes might be expensive, so they need to know what's the bottom line. Are we going to be more profitable in the 10-second condition or more profitable in the 5-second condition? And for that, they don't need to know that the 10-second condition is more accurate. They need to know how much more accurate is that 10-second condition. What is the increase in accuracy that they can expect versus the timeout for 10 seconds or 5 seconds? So that's what we're going to be looking at today. How can we calculate how much of something is there? How much of an effect is there? And that's what we're going to do with confidence intervals. So we're going to talk about estimation in general, and then we're going to take a look at confidence intervals, and then we're going to see how to actually calculate these confidence intervals. And we're going to start with the single sample t-statistic for single sample confidence intervals. And then in the last part of today's class, we're going to take a look at the other two types of t-tests. All right, overview of confidence intervals. Confidence intervals are part of estimation. So estimation is when you use a sample statistic to make judgments about a population parameter. You measure the sample and you try to judge the population. So for example, you measure the sample mean, and from that you try to judge your population mean. When you're doing estimates for confidence intervals, we have to distinguish between two different types of estimates: point estimates and interval estimates. So point estimates and interval estimates, you've been using these in your life before. So a point estimate, well, we just got to get clear on them. So a point estimate is a single number that acts as an estimate for an unknown quantity, right? So for example, if somebody asks you, how tall is your friend, right? Let's say that you're describing your friend and they ask you a question, well, how tall is she? You might say, oh, she, I don't know why I have she was 5.6. All right, rewind. She was 5'6". That is a point estimate. It's one number. It's one estimate. 5'6". That's your estimate for how tall your friend is. An interval estimate, on the other hand, uses a range of values in order to make its estimate. So if somebody asks you, hey, how tall was your friend? You might say, oh, she was between 5'2" and 5'10". So that's a range estimate. Between this much and this much gives you an interval estimate of that unknown quantity. Now, point estimates and interval estimates, they have pros and cons, and they got completely reversed pros and cons. So what point estimates are good at is very high precision. It tells you exactly what that estimate is, right? It's 5'6". It's not somewhere in a range. It's not a low precise, fuzzy sort of estimate. It's a highly precise, high precision point estimate. 5'6", that's your estimate. Interval estimates, on the other hand, have low precision, right? They give you a range. It's somewhere inside that range, somewhere inside that interval. That's very low precision. The cost of high precision is very low confidence. So if you were, for example, let's change the situation here. Let's say that you witnessed a crime and the perpetrator ran off after the crime occurred. Let's say it was a hit and run. So you witnessed a hit and run and the perpetrator left their automobile and fled the scene. Police come in, they're asking you for your eyewitness information, and they can ask you, well, how tall was the perpetrator? And you might say, oh, she was 5'6". If the policeman asks you, are you sure? You might say, yeah, I'm pretty sure she was 5'6". And if they say, are you really sure? You might say, well, no, not really. I mean, she could have been 5'5", she could have been 5'4". I mean, 5'6" is my best estimate, but you have low confidence in that estimate because anything other than 5'6" and you're wrong. If she's 5'4", you are incorrect in your estimate. If she is 5'5", you are incorrect in your estimate. If she is 5'6.5", you are incorrect in your estimate. So your estimate of 5'6" comes with very high precision, but comes with extremely low confidence. You cannot be confident that you are correct in your estimate. On the other hand, interval estimates that come with low precision, that gives you high confidence. So this high confidence here is directly tied into the interval. So if the police officer asks you, well, how tall was the perpetrator? You might say, well, she was between 5'2" and 5'10". And if they ask you, are you confident in that estimate? You can say, yeah, I'm pretty confident. And if they said, are you really confident in that estimate? You can say, yeah, I'm really confident, somewhere between 5'2" and 5'10". And then if they say, are you really, really confident in that estimate? You might say, well, no, I'm not really, really confident in that estimate, but I can get really, really confident if I make my estimate bigger. So if you want me to be really confident, 5'2" to 5'10". If you want me to be really, really confident, all right, 4'10", all the way up to 6'2". Right now I'm really, really, really confident. And if the police officer says, well, I need you to be really, 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 really confident, you can say, all right, I can be really, 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 really confident. She's somewhere between 4 feet tall and 6'10". And if the police officer says, I need you to be really, really, really super duper, massively, extremely, mega confident, you can say, all right, I can be really, really, really super duper, massively, extreme, mega confident. That perpetrator was somewhere between 4 inches tall all the way up to 14.5 feet tall. And you can take that to the bank. I am super confident about that. So you can see that you can get high confidence, but it comes at the cost of precision. The wider your interval, the higher your confidence. Now, we've been talking about confidence in terms of kind of descriptions, right? So scientists don't say, are you really confident? Are you really, really confident? Are you really, really, really confident? We need a way of communicating confidence, and that's what we're going to be doing today. We're going to find out how you can find a range for a specified level of confidence. So you can determine a range where you can be 90% confident that you've estimated correctly. Or if you need to, expand that range so that you're 99% confident that you've estimated correctly. Or if you don't need to be that sure, decrease your range. So you're 80% confident. We can make a range where you can be a specified percent of confidence, and that is what a confidence interval is. So confidence intervals typically are used after you find an effect. So typically a confidence interval comes in after your mean goes into your tails of your comparison distribution. And now you want to know, since there is an effect, how big is the effect? How big is that difference? That's where your confidence interval judgments usually come in the lab. In the real world, sometimes they'll come in when you're doing applications as well. So let's take an overview of confidence intervals before we take a look at how to calculate them. So we have rejected our null hypothesis. Our sample now belongs to a new treated population. And we want to know, how big is that effect? What's the mean of that new treated population? So based on our sample, we want to estimate, what is this new unknown mean? How big was our effect? So in order to do that, we need to put our sample and compare it to that distribution of sample means now from the treated population. So we can use our sample to estimate the sample mean by finding out kind of where is it in this distribution of sample means. because this distribution of sample means has the same mean as your population. So we're basing this on the relationship between the sample and the distribution of sample means. So let's zoom in on that a little bit. Oh wait, before we do that, just to kind of set up the situation, as before, we don't know whether our treated sample comes from the center of our distribution of sample means. We don't know if it comes from the edges of our distribution of sample means. We don't know where in our distribution of sample means our sample came from. That's why we cannot be 100% confident that we've estimated our sample mean our population mean correctly. But we can use this distribution of sample means to calculate that interval. And that's the important part of the confidence intervals. So let's zoom in on this thing. Let's just spread it out. Same distribution, just zoomed in and spread out. And let's take a look at what happens when you end up with means that come from different portions of this distribution of sample means. So there's the mean that you're hoping to estimate. There's your population mean, right? That's what you're trying to estimate. You want to get close to that. And there's your sample mean. And sometimes, very rarely, but sometimes, your sample mean will be exactly equal to your population mean. So this sample mean is your point estimate. That is your best guess for what the population actually is. That is your 5'6" precise estimate. Your sample mean is the best guess, the best estimate we have for the population mean. And sometimes the sample mean will be equal to the population mean. But notice there's a whole bunch of spaces where it might not be equal to the population mean. So what do? Well, we use that point estimate and we make an interval around that point estimate, and we make an interval as wide as the body of our comparison distribution. So we put a certain percentage into the body of our comparison distribution. All right, so let me just draw that out real quick. All right, so we put a certain percentage in the body of our comparison distribution. So we have tails over here, we have tails over here, and we got 90%, let's say, in the body of our distribution. So this is 90%, this is 5%, and 5%. All that adds up to 100%. We've seen that before. What happens when you make your interval as wide as the body of your distribution? So we can see here that when your sample mean, just by luck, perfectly estimates your population mean is in that interval. As long as the population mean is in the interval, that means that you've estimated the population mean correctly. Right? So as long as it's in that interval, you have correctly estimated the population mean. Let's see what happens with another sample. Let's say that that's your sample mean, right? Because again, this is the distribution of sample means. So sample means can come from anywhere in this distribution. This one came from right around there. If that's your sample mean, your point estimate missed. You blew it, you overestimated it, you're wrong. However, with that interval that's as wide as the body of your distribution, this interval correctly estimates that mean because that mean is part of the interval. This is like saying your friend was 5'2" all the way up to 5'10", and as it turns out, she's 5'4". You're right. She is between 5'2" and 5'10". That's a correct estimate. What about for that mean? Point estimate, missed it. Got it incorrect. Interval estimate contains the mean. So this is another correct estimation, another correct interval estimation. This is the estimation for another sample mean. Once again, contains the mean of the population. Once again, a correct estimation. For this sample, that interval contains the mean. For this sample, that interval contains the mean. For this sample, the interval contains the mean. Same thing for this sample. 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 So you can see that for a lot of samples, your interval contains the mean. For all of these samples, their intervals contain the mean. All of these intervals are correct estimations of your sample mean. That one as well. But what about that one? What about that sample with that interval right there? This is the first time that we ended up with a sample where the interval does not contain the mean. This is the first time our interval was wrong. It was an incorrect estimation, did not contain the mean. This is the first time this occurred, and notice that it only occurred when your sample came from the tail. So the chances that you are going to miss this estimate is the same as the probability that your sample is going to come from the tails. So in this case, we had 90% in the body. Our tails taken together were 10%. So in this situation here, with this interval, we have a 10% chance that our sample came from the tails, and therefore our interval is going to miss the estimation of the population mean. We have a 10% chance that we're going to be wrong. That means we have a 90% chance that we're going to be right. That means we can be 90% confident that we've estimated things correctly. That means that we have a 90% confidence interval. So the key here is that we never know which mean we have, right? We don't know which one of these means is the mean that we actually have in our data, the mean that we actually have measured. But we do know that we only have a 10% chance in this case that our mean came from the tail. And only when it's from the tail are we going to miss our estimate of the population mean, miss our estimate of the effect size. So if we have a 10% chance of getting it wrong, we got a 90% chance of getting it right, hence a 90% confident interval. If we needed to be even more sure, we could put 99% in the body and only 1% in the tails. And now we only have a 1% chance of having a sample that came from the tails where we'll make a mistake, hence 99% chance that we're going to get it correct. So that's the basic idea of confidence intervals. Any questions on that at this point? All right. So that's your overview of confidence intervals. What we're going to take a look at now is how do we express that in numbers, and also how do we figure out how big that interval needs to be. Well, it comes down to your formula for a t-statistic. So in general, your t-statistic equals your sample mean minus your population mean divided by your estimated standard error. You'll notice that this is the exact same formula for a z-statistic, except it's using estimated standard error instead of actual standard error. But that's your formula for a t-statistic. Notice that in this formula, there's your population mean, right? We want to estimate the population mean. Well, there it is. It's right there in the formula. So we can get to it by just isolating it, doing a little bit of algebra, cross multiplication, take that population mean over from the right, put it on the left, change its sign, take the estimated standard error multiplied by the t-statistic, bring that over to the right side, change its sign, realize that your t-statistic can be positive or negative, so we put that plus or minus, and there we have the formula for a confidence interval. Your population mean equals your sample mean, that's your best guess, that's the center of your interval, plus or minus t-statistic, which determines how wide your body is, multiplied by your estimated standard error, that's your plus or minus, those are the intervals, those are your arms. All right, so just visually, let me show you this. So in that formula, we had the population mean, that's what we're trying to estimate, that's that value right there. That population mean equals your sample mean. Your sample mean is always your best guess. If you can only guess one number, if you can only estimate one number, it's your sample mean. Your sample mean is also the center of your confidence interval. It's always the center of the confidence interval, and it's your point estimate that's at the center there. So there's your sample mean, and then plus or minus t times t-statistic times your estimated standard error. That's the length of your arms. This is the plus side. This is the minus side. All right, so this is the standard formula for a confidence interval. Now that elections are coming up, you will hear poll results communicated in confidence intervals all the time. So you'll hear something like, oh, approval ratings for this candidate are 30% plus or minus 4%. That's what they're talking about right there. That's a confidence interval in election results. All right, so once again, population mean equals your sample mean plus or minus t-statistic times your estimated standard error. All right, so that's your overview of confidence intervals. And just to kind of give you a sort of numbered example here, let's say that we calculated these values here, and our sample mean was 100 and it had plus or minus 11.5, and our population mean was actually 100. That would be plus 11.5, there's minus 11.5, so you can see that the body of the distribution is as wide as your interval. That would be the situation expressed right here. And again, notice that any sample, as long as it's in the body, its interval will contain the mean and will be a correct estimation. So any sample that by chance happens to come from this body over here, as long as it is in the body of the comparison distribution, its interval will contain the population mean. It will be a correct estimation of that population mean. And it is only when it comes from the tail that you miss your estimation. It's only when it comes from the tail that you get an incorrect estimation, and you control how often that happens by controlling the size of the tail, and you do that by choosing the t-statistic that makes those tails in the body the size that you want them to be. All right, so that's the overview of confidence intervals. Any questions on that before we put this into practice? All right, so you can see that it occurs for both plus and minus tails. All right, importantly, let's put some numbers to this. Let's see this in practice. So the data for this can be found in Excel file 09B, practice June 12th, confidence intervals. So what you're looking for, it'd be helpful if I had it open as well. What you're looking for is this Excel sheet right there. So we got the data for demo question number 1, our terry cloth monkey study. So let's set that up. So once again, we have our terry cloth monkey situation, but this time we're not just looking for is there a difference. This time we have to know how much time do they spend with the terry cloth mother. So the monkey sanctuary individuals, again, they have that virus outbreak. They got all their parents quarantined. They don't want to leave their infant monkeys all alone without some sort of comfort. They want to know how many terry cloth monkeys do we need, because they're working under a fixed budget. They can't go overboard. They want to know how many monkeys do they need so that these infant monkeys can feel comfort. So once again, this is going off of the study that Harlow did, but now rather than analyzing to see if there's a significant difference, so we're not analyzing are the results sufficient to conclude that the monkeys spend significantly more time with the softer mother. We are now looking at how many hours per day do the monkeys spend with the terry cloth mother. So we're going to compute a 95% confidence interval for this. We're also going to compute a 80% confidence interval, and finally a 99% confidence interval. So the 95% confidence interval, that is somebody who is worried about the infant monkeys and a little bit concerned about the budget. 80% confidence interval, more concerned about the budget, less concerned about the monkeys, willing to risk being wrong a little bit more. 99% confidence interval, really worried about those infant monkeys, wants a wide interval to make sure that they have only a 1% chance of being incorrect, not so budget minded. All right, so what we're going to do is we're going to use SPSS to calculate this. And what we're going to see is that this calculation actually can be done and is done using the single sample t-test. So what you can do right now is go ahead and calculate out the single sample t-test. So we have our terry cloth monkeys right here. So we'll copy that and we'll paste that into our SPSS. And then we go down to variable view, and let's change that to terry cloth so that we know what's going on. So there's our terry cloth data. And then if we were going to do a t-test on this, we would go to analyze, we would go to compare means, and we would do a one sample t-test. So that's what we're going to set up right now. We're going to set up the one sample t-test. We put terry cloth in here as the test variable. And that's where we're going to take a pause for right now. So two things that we're going to have to do before we just hit OK. Number one, we need to figure out, we need to remember what confidence intervals did we want. So we're going to start off with that 95% confidence interval. The second thing we have to ask ourselves is what are they asking us to calculate? So there's two possible things that any confidence interval could ask you to calculate. First is how much of something is there. Secondly is how much of a difference between two things are there. So sometimes you want to know how much of something is there. Sometimes you want to know how much of a difference is there. And you need to identify which one of those is being asked before you calculate your confidence interval. So for example, here, they are not asking how much more time are these monkeys going to spend with the terry cloth mother. They want to know how much time do they spend with the terry cloth mother. So when they're asking for how much, for the single sample t-statistic, what you want to do is when they're asking for how much, when they're asking for an actual amount, keep that test value 0. Because you want to know how much is there of something. What that means is that you're comparing your scores to 0. Right? So if somebody asks you, well, how much money do you have in your bank account? You're not going to ask them, well, compared to what? Compared to $500? Compared to $1,000? Compared to $20? What do you want me to compare it to? It's implied that when somebody asks how much, you're comparing it to 0. So in this case, if somebody is asking you, how many hours do they spend with the terry cloth mother? We're not going to put in that hypothesized value. We're not going to put in that test value of 9. On the other hand, if they ask you something like, well, how much longer than 9 hours do they spend with the terry cloth mother? We would update that test value to 9. But as it is, they're asking us how much time do they spend with the terry cloth mother? So we're going to keep that test value at 0. All right, last thing we need to do before we let this go is we got to click on options over here. So we've never clicked on the options button. Now's the time that we're going to do it. And you can see that in this options, there's really only one option, and that is your confidence interval percentage. So when you're calculating confidence intervals, that's where you want to go to. And you want to enter in the confidence interval that you've been asked to calculate. The default number is 95%. Just like an alpha level is usually 5%, confidence intervals usually 95%. So that's going to be the default. Luckily, that's what we want for this first question, so we're just going to keep that as is. We hit continue, we hit OK, and we get our one sample t-test output. And I'll show you how to read this in just a second, but I'll just show you right now, right there, we have a 95% confidence interval of the difference. SPSS has calculated a 95% confidence interval for us just when we ran that t-test. So let's do this a couple more times because we were asked for 3 confidence intervals. So we just calculated the 95%. Next one we're going to do is calculate the 80%. So we go back to our data input here. We go back to analyze, compare means, one sample t-test. It's already set up for us very nicely, but we have to go to options. And now instead of 95, we're going to do an 80% confidence interval. So we change 95 to 80. We hit continue. We hit OK. And SPSS has now calculated an 80% confidence interval right there of the difference. All right, one last one, because we were also asked for a 99% confidence interval of the difference. So let's go to that. So we go to analyze, we go to compare means, we go to the one sample t-test, we go to options, change our 80% now to 99%, we hit continue, we hit OK, and we now have our 99% confidence interval of the difference. So confidence intervals are calculated when you do a t-test. You just need to go to the options and let them know, let SPSS know which confidence interval it is that you are that you're looking for. All right, so we've got numbers now, but we need to figure out what they mean and how to actually use these confidence intervals. So the SPSS analysis is all done, but now we need to figure out our actual confidence intervals, and importantly, we want to get them into the format that most people use. And the format that most people use is your estimate equals something, your mean plus or minus t-statistic times your estimated standard error. We want to get it into that plus or minus format. And that's one thing that SPSS does not do for us. But let's see what SPSS actually does. So there's our output. And very nicely, sometimes you're calculating a few confidence intervals. Very nicely, SPSS labels what the confidence interval is in each table, just in case you lose track. Now you'll notice that I mistakenly put in the test value here. So that's actually a good thing because you'll see what you have to do, just in case you do that on your own. And it'll highlight the difference between what they're calculating. All right, so when you're looking for your confidence intervals, if you were doing this by hand calculation, although I don't know why you would, if you're doing this by hand calculation, that estimated standard mean right up there, that is this value right here. So that value, 1.73, that is your estimated standard error. So that's where you would find that particular piece of information. There is your degrees of freedom. Your degrees of freedom are going to be used to look up your t-statistic if you need to do this by hand. Again, so SPSS has calculated this out for you, but that t-statistic would be looked up using those degrees of freedom. Importantly though for us, it's already calculated the confidence interval, but it's given it to us in terms of upper or lower bounds. So we have the lower amounts, we got the upper amounts, and we got the mean difference here. Your numbers are going to be 9 points off of my numbers. So for your mean difference, you should have a mean difference of 15.3. For your lower estimate, that should be 11.3. For your upper estimate, that should be 19.29. So what I need to do, because I kind of messed it up, is for the mean difference here, I need to add in that 9 hours that I took out to get to 15.3. For the lower, I need to add in those 9 hours that I took out to get 11.29. 11.3. And for the upper, I need to add in those 9 hours that I took out to get 19.29. So this is the output that you have. If you make the mistake of putting in the test value when you're asking for actual amounts, you're just going to have to add it back in. It's not a big deal, but why do that extra work for yourself? Let's try to get it right the first time. All right, so now what do we have? We have our 95% confidence interval of the difference. Starts with the mean difference. This right here, that is the center of your interval. So 15.3 is the center of your interval. 15.3 is your point estimate. When that monkey sanctuary asks you, how many hours do these monkeys spend with the cherry cloth mother, your best estimate is going to be 15.3. That's your point estimate. Now, the interval for that goes all the way down to 11.31. I'm going to round that off to 2 decimal places. Goes all the way down to 11.31, all the way up to 19.29. So we are 95% confident that these monkeys are going to spend somewhere between 11.3 hours all the way up to 19.3 hours with the terry cloth mother. But notice that this is not in this format. So the mean is going to be that number right there. So this M is that. So we want this in this particular format. We want it in that 15.3 plus or minus, and that plus or minus is the size of your arms. It's the length of your arms. And the easiest way to get to that is to take your upper limit and subtract your middle, your point estimate. That will work every time. It'll work for positive numbers, it'll work for negative numbers, it'll work for when this is positive and this is negative, this is negative and this is negative, this is positive and this is positive. It'll work in every single situation. Take your upper limit, subtract away your middle part, and that'll give you your plus or minus. So we got 19.29 minus 15.3, that's 3.99. So we are 95% confident that these monkeys are going to spend 15.3 hours plus or minus 3.99 hours with the terry cloth mother. All right, so again, SPSS will give you upper and lower bounds. It will not give you this format that is most widely used. So we need to do just that little bit of math, that little bit of addition and subtraction, a little bit of logic, and we circumvented this. So you don't need to take a look at all these slides because we actually didn't take out the 9 the first time. So if you did, then you would have to do what I just did right here, which is add those 9 hours back in to get the 15.3 hours. But this last little thing I want to point out, your 95% confidence interval, we just calculated that right here, 15.3 hours plus or minus 3.9 hours. You can be 95% confident that the amount of hours that the monkeys spend with the terry cloth mother is actually in that range. If you want to only be 80% confident, your range goes down. Right? So now we got 15.3 plus or minus 2.42 hours. If you got to be 99% confident, your range goes up to 15.3 plus or minus 5.81 hours. So the size of your interval is directly tied into the confidence level. The more confidence you need, the wider your interval has to be. And you can, just as an exercise, try to get these numbers here based on the output that we just calculated, just to practice this center of the confidence interval. Notice all of them are centered on the same sample mean, on that same 15.3, and then practice how to get the length of each interval, because that length changes depending upon your confidence. All right, so that was our sort of intro, our first look at confidence intervals. What we're going to do right now is we're going to take another break. So let's break until 11:30, and then at 11:30 we're going to see how to do confidence intervals with independent means t-test and also with dependent means t-test to round out those three possibilities. All right, so we will come back at 11:30 to finish today's class.